Okay, I think people will start coming in, but let's get started because we are just after 3. Welcome everyone. I'm Sharon Clarence from the Center for Postgraduate Studies, and we're very pleased to have Professor Horst Kaiser with us this afternoon, who's going to be talking to us about research design. I'm going to let Horst tell you a bit more about himself in a minute. Just to say that this session will be recorded for our records, and also just in case there are people who wanted to be here but were unable to because of clashes or connectivity issues. And then to remind you that you need to please keep your microphones on mute so that the noises in your background don't interfere with the recording and the audio. And you may use the chat function to ask questions or pose comments throughout the seminar, and we'll be keeping an eye on those. So thank you very much for being here, and over to you, Horst.
Thank you, Sharon. I hope you can all hear me okay. And
yes, we can.
I must say personally I miss those days when one could see each other and there would be interactions and somebody would maybe shake their heads and say, no, I'm not understanding this, or somebody would nod their heads and say, yeah, I agree with that, etc. So this is obviously a whole different thing for me. I remember years and years ago when I went to the normal library there up in the hill at Rhodes, and I wanted to look up something on research design. And I found a shelf of books, you know, the old books that you can still hold in your hand and you page through them. And I saw these, and there was literally shelves of just statistics and research design issues that were discussed. And now I'm sitting here and I think, how can I possibly do justice to that amount of enormous knowledge that is sitting in this literature base that we have? And the only thing that I can do is actually to talk a little bit of also from my own experience about research and what I find from my experience, what has been valuable to do and what has been important to consider when you design your own research projects. For some of you, you're probably at the beginning of your projects. Some of you might sort of be in the middle of data analysis, and maybe others are happy to or feeling lucky that they can start writing up, which is kind of the fun part at the end of the day. So my concept or my idea today is not so much that I will be able to give you all kinds of answers to everything. And it's also going to be difficult to find the kinds of examples that is good for everybody. I will have examples from the natural sciences and and a little bit also from social sciences, humanities, so that we have a little bit of everything that we can talk about. So why did we meet today? At the end of the day, the most important thing that we might want to take home is that a good experimental design makes the data analysis a lot easier. A well-prepared experiment is the one that you lay out properly and that you design in such a way that when you get your data, you will be able you will know exactly what you want to do with them. It's easier said than done, and this is probably also the part of your project overall that should not be rushed. You take your time for this, and you consider a whole lot of aspects of it, which are actually going to be part of this talk today. So only an experiment that can be repeated or reproduced is publishable or even acceptable in the long run. What I mean with this is that any kind of experiment that you do, any kind of design that you put together must be explained so well with the methods that anybody else is able to reproduce or repeat it. Easy to say this because you do your methods and do your experiments, and you might sometimes think that there are certain details that might not be important or that shouldn't be reported because you already do this anyways. But as long as you provide the methods of your experiments in such a way that they can be reproduced in principle, you would have already done a very good foundation for your study. The next thing that is to be considered is only a clearly stated research objective that is motivated well is the foundation. for a successful experiment. So these are the things that we will start with and that we want to take a bit of time to think about. And what can you make how can you make your contribution to your specific field in which you work? And obviously the big thing first is to review the literature, and do not maybe also don't forget the older papers. I've often seen manuscripts that came across my desk, and I've seen reviews of manuscripts of others too. And sometimes an examiner or reviewer would say, this is really interesting research, but did you actually see in 1960 somebody did all this? But it wasn't actually properly indexed on Google yet. So sometimes make the effort of searching in references a little bit deeper and see that you make sure that you have covered your field, even those older papers that may not all have been properly available at this point. And so you identify what your project will add to the existing knowledge of the topic if you do it like this. And that's very important because you do want to be sure that you don't simply repeat something that's all been done, and then in the end you feel like it was worth to do it, but it wasn't maybe so exciting that you can tell somebody else what's really new and what's special about things. So how can I contribute today to your work? We've just discussed how you contribute to somebody else's work. So what I can do for you today is I will share a few ideas with you, and I've picked out some things that they're not actually so easy to find in the books, and some topics that might take chapters and chapters to go through, but maybe I can try to see whether I can summarize a few things and highlight the most important parts. And I'd like to do a short excursion for a few minutes as we start in a moment. And I'll start briefly by discussing what's actually science in general and what is research and how do we actually view it and see it. And once we've seen that short detour, we have a kind of a basis for our own research designs as well, and particularly for the method section that I find quite important. So some of it that I will present here is based on my own experience, because I have a course in which I teach research, and therefore I don't have a lot of references on my slides. If I obviously have to reference something or somebody, I will, but it's mostly ideas that I've put together over the years. I hope you understand this is not a seminar on statistics. It never can be, because we have fantastic lecturers at that do a really great job at teaching statistics in a way that I probably wouldn't be able to do as good as that. But the overall ideas and the concept of how we do research design is still something that we can discuss together. So let's do a short detour. We know of science, and science is often seen as kind of the big answer to everything, the ivory tower, and once upon a time in 1969, when people managed to send some astronauts to the moon, that was a time when science was so much in the public eye, and it was such a big thing that everybody knew something about it, and we still obviously know today. So it was a very public kind of science. It was research that was directly connecting to what we know today and what we see today. Interestingly, there's a picture here on this slide from the so-called Atomium in Brussels in Europe, and it's a massive building that weighs about 2,500 tons, and it is a 160 billion times magnification of the iron crystal. Those were big days, because people have found some really exciting stuff. And whether it's applied science to a large extent, like, for example, sending somebody to the moon, or whether it's observation science, like say, finding out the structure of the iron crystal, it's all based on one thing, and that is good preparation of what you want to do, good research objectives, and the ability to also sell that further up in terms of make reproducible methods. So here's an interesting quote that I found, and that was in 2004. I'm going to read it as a quote. In Britain, the Minister of Science wrote to the particle physicists, in 30 lines explain why British taxpayers should invest a substantial part of their resources in Higgs boson research. There was a chance. There was a chance for physicists, for example, to score big and to actually sell their topic and produce something that was going to be interesting for everybody. But interestingly, at that time, they actually failed doing this. They couldn't really, they struggled to get their research objectives right. And yet, at not too much later, $3 billion were given to stem cell research. And that is an example of, there was so much activity and so much general publicity going on there that the whole world was interested in a certain topic that meant something to them. And even though there were sometimes research objectives that may not all have been as clear as the ones that the physicists would have had, the selling point was better. And so at the end of the day, science for us is actually something, or research, if you like to put it that way, is an activity which means that we have to both sell our research first in terms of motivating why we do something, and also then presenting afterwards what we have found. Let's look at Charles Darwin, and let's look at Watson and Crick. In the case of Charles Darwin, his book on the origin of species was a volume of about 200,000 words. You can imagine what that would be today if you were asked to write an essay. And 94 years later, Watson and Crick discovered the double helix of our DNA molecule. And they managed to actually put their original thoughts and their first thoughts together in less than 1,000 words. It's not even one page. And so our way of communicating has changed a lot, because in one case, a big concept was produced, say Charles Darwin, if you like. And in the other case, there was a very meticulous planning that had very clear objectives. And it was then possible to put this together in very few words to sell to the rest of the world one of probably the best papers written in biology on DNA. So ultimately, when you put all of these things together, what would be, or you can imagine for yourself, what could be the biggest secret of a success in a research design, in a research project, and with regard to your research design? What is the one thing that is potentially going to do your make and break, that also means that you have lots of fun and that you can enjoy what you do and where you go from there? And that is the concept of ownership. In my opinion, and also in my experience, the concept of ownership is the one underlying thing that is extremely important. I cannot overemphasize this enough. Own the project. It's yours. Go for it. Run for it. Do what you need to do. Follow the rules of the design, which we're going to do now, and make sure that it's always yours. And I think that in itself will be the biggest cornerstone and the biggest foundation for going from there and having successes in your research. There's in my view, there's nothing that comes close to this. So let's talk a little bit about the so-called research objective. This was not unknown. Even the old philosophers, Seneca in 8 BC, he made it quite clear by thinking about his tasks, and he was saying, like, our plans fail if we don't have an objective. Then we don't know where we're going. If one does not know to which port one is sailing, no wind is favorable. So the research objectives is a major issue, and we will be spending some time on preparing the concept of it, because it goes much bigger and it goes much further than just having an objective of, say, 1 or 2 sentences. It also has to do with, they have a slightly broader background as to where this whole concept of hypotheses and objectives actually really comes from. So what is this thing that we call science? There will be many answers to this, and probably the one thing that could describe it quite well is it's an objective method that's supposed to be reliable, and it should prove, or it should show a way to obtain knowledge. The word scientia in Latin is actually translated directly into knowledge. So this is what the ultimate idea is about. And even today, but particularly since scientific investigations started, it was based on a concept of inductivism. And that means that we go from a statement to a generalization. We find something, we find it again, and therefore eventually we come up with a kind of a generalization to say, this is what we think is going on. And this follows a certain set of rules. So the number of observations that you need would be large, otherwise something would be just a coincidence. You see something once and never again, and that's not going to help you, because then nobody else will be able to confirm it with you, and you have to have a large enough number of observations to be sure. The issue of sample sizes will be discussed later again, but this is like the underlying concept of the inductivist rules. And it must be repeatable. You must see something once and again, and the more you do, the surer you get that you are right about your observations. Yet, and this is where one of your problems lies, just about any observations you make, whether it's in humanities and science and social sciences or anything else, it should, strictly speaking, not have exceptions, but yet it does. So nothing has no error. Everything has a variability to it. And there's your first kind of weak point of the starting point of inductivist rules. And that is that you do not really initially allow exceptions. So the principle of induction is actually quite a simple one. It means that if a large number of something, of an observation has been observed under some conditions, then if all A's possess a property B, then all A's have that property. So this is a very stubborn way of operating, because it completely ignores that not everything is always the same all the time. The concept here is you acquire some facts through observations, then you have your laws and your theories, and you have your predictions and explanations. This is the inductive, deductive reasoning that we know. There is still a lot of good things about it, and we do work like this these days as well. But later we will discuss concept of hypotheses in that context, because in this context we want to see what is actually a good observation and how can we be sure that what we find we're actually comfortable in presenting further. So the process of deduction is actually a relatively simple one. It is built on a premise. For example, say all seminars on science are boring. If this is a seminar on science, then the seminar must then by default be boring. If the premise is correct, in other words, if the premise is accepted, then whatever is the conclusion later is actually not anymore questioned. And this is crucial, because it's a very direct way of operating to do induction, deduction, come to a conclusion, and you're done with this. But if we put the inductivists on a trial, then we find out that the method that is used in those simple ways doesn't handle exceptions. And it isn't, as you saw in previous example, it doesn't have to always be logical. And the idea of how much is a large number of observations will never be quite clear, and it will never be, and we can never be satisfied with this until we find new compromises. And we cannot do anything with confounding factors, which I'll discuss at a later stage anyways. So from here, one or two more slides before we go further, Karl Popper in who was born in 1902, lived until 1994, he came up with a new, slightly more refined concept of this, and he talked about falsification. And for Karl Popper, falsification was basically to say you are allowed to make a statement about anything as long as the statement can be questioned or falsified with other information. This Karl Popper's approach to science has actually been very instrumental for a really long time and still is today, because it goes one step further and it tells you about your hypotheses in their early stages about what you can actually state and what is an acceptable thing to say. Here's an example. It never rains on Wednesdays. I can make the statement, and that is a very acceptable statement because it allows you to falsify me. It allows you to throw it over because you just simply wait for that Wednesday when it does rain, and then you come back to me and say, well, see, it was a good statement, but at least it allowed me, it gave me the permission and the possibility to falsify it. Another interesting example from my own field is all fish breathe oxygen dissolved in water. Fact is that is not really true. Not all fish do. And so therefore the statement is fine because it is falsifiable. It can be overturned. But a bad example of falsifiable statements is like, for example, either all students will pass the exam or some will fail. That's nonsense because it tells us absolutely nothing. It confirms nothing. It has no information. And it can't be falsifiable because if they fail, if I'm wrong, if they don't fail, I'm wrong. So nothing comes from it. And a second thinking example is one that is more subtle and a bit more difficult to understand. And that is that if we state that all points on a circle are equidistant from the center, we're actually stating a complete and properly understood definition. There's no more room for anything else. So this is actually not such an example of what is falsifiable because that is the set thing. That is in its definition what a circle is. The way forward from here is we will discuss some of the most important aspects of experimental design and also some of the important definitions that we need to know. Most importantly, at the end of the day, is knowing what types of data you work with when you do any kind of experimental design or data analysis. And knowing the types of data you work with is so important that it actually makes and breaks the foundation for where you go from this point onwards. You would have by now certainly heard about categories of data, about continuous data, about discrete data, and so on. And anytime you design an experiment, you want to look at what the data is going to be that your experiment produces. Say if you were to compare simply the height of people from different parts of a town or something, doesn't really matter. It's just a very arbitrary example. That would be an example of continuous data. And then with this, it's already set to a large extent what kind of statistical test you will be using from then onwards. And hopefully, if we go through nicely now, then we will design some basic experiments together, and we will discuss a very important aspect of it, which is the concept of bias. And I'll have a few thoughts about writing after that. So what do we need to know? Earlier, I mentioned to you, we need to have some idea about what are treatments, what are replicates. A slightly less well-known word is the term experimental unit. And also what are the variables, what are variables and effects, factors, covariates, measures, repeated measures, and what do we mean by residuals? And more importantly, actually, we have a little bit of information later on numbers and their particular units. That last one is a particularly relevant one because I know from my own experience and I see how often numbers and units can actually be confused, and I will give you some examples for that. When you find yourself with a data set that you will be producing as a part of any kind of experiment, say a survey if you like, or measuring the habits of people, or anything that has to do with animals if you like, then you will always be confronted by the big question: what kind of statistical test should I be using to analyze the data? That's actually a very challenging task to do, and I've come up. I'm daring. I'm putting together some courage here, and I'm taking a bit of a risk. But I'm daring to give you one slide that actually summarizes a large part of this question, and I'm going to have to guide you through this because it might then be an opportunity for you to see the picture that I'm trying to draw. Anything that we do is an interplay between what we call dependent and independent variables. Later on, for example, I got some situations where, say, we feed animals a certain kind of food, and then we'll see how well they grow. So the independent variable is how much food we feed them, what kind of food we feed them, etc. And the dependent variable is what happens then. In other words, it depends on what we do to the animals, or what kind of original data set we have. And that would be the growth of the person or the animal or anything like that, that is an outcome of the independent variable. If you can manage to keep these two terms in your head, and at any time in your experimental design, or at any time when you do data analysis, you should be disciplined and force yourself to go right back to that one specific starting point and say, what are my variables and which is the independent and the dependent variable? That's extremely important. Each of those, the dependent and the independent variable, belong to a type of data. It can be categorical data, frequencies, distribution, continuous data, discrete data. It doesn't matter. Each of them have a specific type of data attached to them. And if you do experiments that you plan very well, then you have a number of treatments and replicates as well. So the combination of knowing your variables and knowing your types of data and knowing your number of treatments is a big step towards finding the statistical test that you need. There are some of the statistics books that you find that will have flowcharts in which they guide you through one step at a time as to what is a good test for a specific data set. But if you start with this type of approach, you get a long way. You get quite a long way, actually. You can achieve quite a bit by just keeping those two rules in mind. What type of data do I have, and what do I identify as dependent and independent? That is it. From then onwards, the rest will kind of start falling into place. It's not perfect. There are some analyses that become a little bit more complex and complicated. We'll discuss some of those. But for now, this is a very good starting point. So I will talk for a few slides about experiments in natural sciences, in this case, for example, experiments with the use of animals to test certain things. And I'm doing it because this is for now, it is what I'm particularly used to. But we will have other examples from different kinds of disciplines after that as well. So I hope you'll be able to stay with me until some things come up that are particularly useful and interesting to you, and that you can benefit from. So when we work with animals, for example, then our most important thing is that we decide that we use as few animals as we need and as many animals as we do need in order to get to some good answers in our experiments. Using too little is just as much a waste, because then you don't get good answers. Using too many is also not acceptable. So we have to sometimes find new ways to reduce the sample sizes and to control confounding factors. I call them here nuisance factors, but they can also be referred to as confounding factors. We have to have a good idea about what randomization means, and we have to have some idea about what sample size we actually need to work with. This kind of the answer to this comes to a large extent from knowing the variability of the data from a certain specific set of dependent data. And we have to understand what is replication. What follows now is, I hope you will agree, it's relatively simple, but it is a way of setting a foundation for the terms and phrases that we use. And without that, we will have a really big problem later to design experiments of any kind. So I'm going to start very simple. We test the effect of a drug on blood glucose levels in rats. That means that we have, in this very simple example, we have some animals that are being given a drug and some animals that belong to a control group that don't get a drug. And for each of those, we have replicates for each treatment. And for this super simple example, we have 2 replicates per treatment. Ultimately, in the real scenario of doing a good experiment, 2 replicates per treatment is not enough, and it is not what is usually being accepted in the literature. But for the sake of having our definitions and for the sake of actually just understanding why we do, what we call what, I've just kept it to 2, just to keep it simple. So what is our definitions? The effect of a drug is our effect that we're testing. Then in terms of treatments, we have 2. We have drug and no drug. And in terms of replicates, we also have 2 per treatment. So 2 by 2 is 4. That means we have 4 boxes or cages altogether. This is the simplest kind of experiment that you can kind of design in this context. Let's go and apply some of our definitions to the exact same thing again. And that is, we have the independent variable, which is the presence or the absence of the drug. And we have a dependent variable, in this simple case would be blood glucose levels. So this doesn't differ from the previous page. I'm slowly adding like 1 step at a time as to how we find our definitions for something. So what do we have here? We have 2 treatments, drug, no drug, and we have the 2 replicates for each of the 2 treatments. Now it gets a touch more complicated, not so much, but a little bit. And we're going to have to ask ourselves how we design this experiment with regard to sample sizes. So we still have 2 treatments, we still have 2 drugs, and for each of the 2 replicates, we're going to have 10 animals per replicate. So that means that we have now done or designed an experiment in which we altogether used 40 animals. However, when we do the statistical analysis of such a data set, we still have only 4 values that we will be using to do an analysis. And that is 1 value per replicate per treatment. Because the 10 animals that are kept under the exact same conditions, in the exact same housing, for example, and under one solid in one environment, they would have, their values would have to be averaged before you can continue with the analysis. Because if you don't average them and use all the values, you would simply overemphasize or amplify whatever small differences you have between your treatments. You would assign too much value and too much weight to that. So, and this is actually something we refer to as pseudo replication bias. And that is that if you replicate a certain test on any subject, you will have to make sure that you take care of the fact that you know what you must average before you do an analysis. So by adding more animals here, we will potentially get a much better average for each replicate. But for the analysis itself, we're not scoring here because it will still remain to be 4 experimental units. And now I've sneaked in another definition, and that is the so-called experimental unit. That is the one thing that will come out of this that goes into the analysis for your data set. So what is the problems? What are the problems with the design that I've just been presenting to you? Well, the first thing I've not done is I haven't given you any hypothesis. I've done it on purpose because we're going to discuss the hypothesis as we go along. The number of replicates are very small. So it was just an idea of what we do and how we lay this out. And I've not discussed with you how you would randomize samples, but we did understand the idea of pseudo-replication. And some other confounding factors that may be discussed, we will do in later examples. So for now, I have been far from complete by actually giving you the right design, but we have to start with some point. So how do we solve this? Earlier, I said to you that maybe we can get away with as few animals as possible, and maybe we can refine our experimental design a little bit better. Perhaps we can have fewer rats per cage, but more experimental units. That's option 1. We have, again, drug, no drug, and we have now 1, 2, 3, 4, 5 replications. Oh, I see there's a type where it's rep 4 is given twice. So that's 1, 2, 3, 4, 5 reps. And we have only 4 rats in each. That means we have now got 2 treatments with 5 reps each. That is going to be 10 experimental units. That's a much better design than the previous one because it increases your sample size right there without, interestingly, using as many animals. Another option would be that you have to ask yourself what your research question is. And sometimes you may have designs, and you'll have them in all disciplines, where you have what's called the repeated measures. And in the case of a repeated measures, you take a specific subject, or maybe a cage of animals or something like that. You will take this and you will be measuring repeatedly. In other words, say you measure the blood glucose level on some animals first, then you give them a drug, and then you measure it again. If you do this approach, you will again need fewer animals because the same animal is actually part of both treatments, but it is a repeated measures design, and it allows you to answer rather different kinds of research questions that allow you to control the variability within the animals much better. Not for all experimental designs is this possible, but this is an example. And if you ever do a design that includes repeated measures, you may also have to sometimes consider whether the assignment of a treatment should be reversed. In other words, maybe you should first feed the drug and then test again after some time when the drug maybe have worn out. So you can go from top to bottom or bottom to top. It's either way. It's possible, but the reverse order should not necessarily be forgotten. The block design adds an extra element to this, and that is that it allows you to sometimes control for additional factors, like where in a room you keep your experimental designs, how you, in what sequence, and how you randomize something. And it allows you to test how many, it allows you to test for each experimental unit, what other effects may have played a role in your data. And finally, the randomization techniques are probably one of the most important thing of just about any experimental design. And that is that you always try as much as possible to randomize any samples that you take. Or you allocate, for example, experimental units to a bigger environment in such a way that they're equally allocated, so that you don't have just one effect working on them. An interesting example that has often been described when it comes to randomization is that sometimes a large number of animals is available, and you want to test, say, for example, their behavior. And then somebody comes along and takes one animal out, the next one, the next one, the next one, and then assigns those animals to a certain treatment. Then after a while, there is enough animals for this treatment, and you will then assign the next group to the next treatment. But maybe the first few animals that you take out were by definition or by default the most curious ones. And then you don't know anymore whether you test the treatment or you test the kind of predisposed behavior that those animals had before they even started. So randomization is basically a way of saying you take the first one to one treatment and randomly the next one to the other treatment, and go on and on and on like this, to make sure that you don't have additional effects that they're going to be messing up your data set. So this is randomization is a very important part of the of good experimental design techniques. So these block designs, they have advantages and problems. They may influence your study, because sometimes you can spot issues when analyzing your data that may have had an additional effect. And you can also you can have results that lead to the need to repeat the experiment, perhaps because randomization was quite clearly not doing justice to the need to assign your treatments as your replicates to treatments in the right way. I have initially overlooked or forgotten to mention the idea of hypotheses, which is important enough to bring up next. So what is this so-called famous p-value? The p-value has become a part of our daily research activities, and it's perhaps the one value that everybody is particularly interested in. Let's use the previous example. Let's say mice in one treatment receive a drug while the control treatment does not. We test the red blood cell count in both treatments. The statistical test that we use is designed and assumes that our data are following what we call the null hypothesis. And the null hypothesis is that the average value for the drug and the control treatments are the same. We then do our test. So we crunch the numbers and we get a p-value. And then there's big excitement and we get a p-value that's below 5%. We all understand that that means that we found something significant. I will discuss later with you why, strictly speaking, we can't get too excited about this, because finding something that's not significant can also sometimes be very interesting too. But we'll keep with this for now. So I'll repeat this one more time. We do our test. We find that we get a p-value below 5%. What this basically means, and I'm going to read those 3 lines because it's easier that way. What this basically means is, in this particular case, there was a chance of less than 5% that you got a result as extreme as the one you actually observed, given the null hypothesis. Therefore, the chance that the data are supporting the null hypothesis would be very unlikely, because it's a very small chance. So it's only a 5% chance that this really did happen. And therefore, it is a significant effect, and we have the basis for favoring the alternative hypothesis, which means then that these 2 means are actually significantly different from each other. This is what the p-value basically tells us. So at this point, you will ask yourself, why are we so stuck on this concept of a p-value? And to answer this, or to go back to this question one more time, is we can literally go through all the slides all the way back to the front again, from induction to falsification, etc. And it's all about the question whether something is actually reliably different, or whether something can be reliably repeated, or whether we have a good answer to our research question. So a p-value below 5% identifies that whatever you're testing shows significant effect of the independent variable on the dependent variable. There's your core part of your statistical tests, and that is then directly linked to the hypothesis idea. A few more thoughts on this. Perhaps more important than you might recognize is whatever your hypothesis, whatever hypothesis you will be setting for your experiment should be developed before you start it. If you get a lot of data out of a study, and you then sit down and you develop a hypothesis for these data, you have already seen them, and it's quite possible that your hypothesis will just be correct by default, because you know what you're looking for, and therefore it's not really a good point in testing that. So if at all possible, the hypothesis must be developed before you start the study. Very crucial. And another important part of any study that you do, whether it's surveys or whether it's studies on human behavior or anything like this, one should not forget that you had an initial research design plan, and you should stick to it. You shouldn't, for example, consider that you might want to drop collecting your data because you've gotten what you thought you'd be getting, or you have confirmation of what you think you should be getting. The research design in itself is crucial. It's very important for you to stick to that, and to make sure that you are loyal to what you've actually designed your experiment for. let's do a couple of tests. I've been testing in my previous slide, I've been testing the hypotheses in such a way that I explained the null hypothesis first. And here's an example, a very arbitrary example, but hopefully it's a good enough illustration for what I wanted to show you. Is that, let's say we compare per capita consumption of vegetables for two groups of consumers. One group lives in an urban environment and one group lives in a rural environment. We call them U and R. So our null hypothesis is that the average per capita consumption for these two environments is equal. And one possible alternative hypothesis is that they're not equal. This can mean a number of things. It can mean that one is larger than the other or one is smaller than the other. But for now, we just say it's not equal. If we go back to the previous slide and we say that we have tested our null hypothesis with the respective test that is a good idea for this data set, and we find a p-value of less than 5%, then we reject the null hypothesis and we accept the alternative hypothesis, which means that they are not equal. But this is great because if you already have your averages for each, then you can immediately see which is larger than the other one. But it is reliably larger if the p-value is less than 5%. And the next example is just a little bit more complicated. And in this example, I'm using the same design one more time, and I'm comparing three groups with each other: urban, rural, and suburban. We once again have a null hypothesis which states that all three means would be equal. We run the respective test, and a possible suggestion here would be something like analysis of variance. And we now have to discuss what we understand as being the alternative hypothesis. And the alternative hypothesis is not to say that they are not equal, because that isn't really very useful information. The alternative hypothesis would be that at least one of the means differs from one other. So I've given a few examples on the smaller writing at the bottom. In other words, it could be U is larger than R, but the same as S. U is the same as R, but larger than S, and so on. These are the possible outcomes, but the alternative hypothesis will always be that one mean differs, at least one mean differs from one other. A special case that must be considered in this context is the relatively a slightly different kind of way of approaching things, and that is regression models. Let's take the example of a simple regression model. Mostly a regression model is, I'm going to show you the next slide so we can see it right away. A regression model is a way of making a line of best fit through a data set. And here in the bigger of the two graphs, we have the individual points that belong to the dependent variable, which is the y variable, and we have the independent variable, which is the x variable. In other words, back to my original definitions, the y variable depends on x, so that's the dependent, and x is the independent variable. We have all these points, and we calculate the line of best fit through those points. The regression model itself would say something like y equals an intercept plus a slope times x. And if we do this and we have a significant p-value for slope, in other words, if the p-value that tests for slope is less than 5%, that means that the slope is significantly different from 0. If the slope of a model like this were to be 0, then the blue line in your picture would be parallel to the x-axis. And then it would not be a significant regression model in a way of that it actually allows you to do any predictions. So our null hypothesis mostly for regression models in the simple case would be to say that the slope that we test for the slope of the model. Now have a look for me at the smaller graph on the bottom. It's once again a data set, and again I've been drawing a blue line here, that is the line of best fit. But if you kind of very carefully explore this further, you will probably disagree with me quite easily, and you will probably say, no, this is not a line of best fit, because in the first part of the graph between points 5 and 0.7, it always underestimates the points, and later on there's a whole section where it overestimates the points. So a good regression model is actually the one in which the distribution of the points around your line must be as randomly distributed as possible, so that at no point you will either under or overestimate. And this is what is also referred to as the residuals. Earlier on, I gave you a hint about saying that we wanted to talk for a few minutes about what we call numbers and units. And this is quite definitely one of the most crucial parts of any data analysis, or any even any experimental design, if you like, because it is about as easy to work with units as it is difficult. And this problem of working with units is it's not only a problem for science. It's also a problem in everyday life. Look at this advertisement. It's an advertisement for a granola bar, and it says, the company says, we wanted to increase deliciousness by 200%, so we put 2 bars in each pack. The comment here below is, so does that mean that the second bar is twice as delicious as the first one? What happened here is that whoever puts this advertisement together, it didn't actually work with the right definitions to start with. Because the concept of what is delicious or not is not well defined to start with anyways. And also the unit is completely wrong, because by adding more bars, they're as delicious as they were before. So we can easily mix up units very easily, and it can become quite messy. Here's another example. Have a look at this. We'll look at it together. A company made a funding organization made a big advertisement to say 1/3 of our operating budget goes towards financial aid. So 20 million goes into financial aid, 60 million is the rest. So 20 million is 1/3 of 60 million. No, it's obviously not, because it's the 1/3 of the total that we're interested in. So it's very easy when it comes to units to get confused. And so not only in everyday life do we have this, but also in our way of dealing with scientific experiments, where we sometimes forget to mention properly what kind of unit we're actually referring to. This brings me back to when I was a student myself, and we had a lecturer in my university who always told us that when we do presentations and we go onto the board and we write numbers there, that the numbers should have units behind them at all times. And the first group of us that went up there wrote up some numbers on the board, and we didn't put the unit behind it. And the warning that we were given beforehand was actually quite correct, because the lecturer actually went up and left and said, "I don't understand you any longer. Without your units, don't talk to me." So we learned the hard way how important units actually are. The last one of the units that I found kind of interesting was a picture that I made some time ago at an airport. Let's have a look at this together. Carry-on baggage may not exceed one piece, 70 kilograms, fine, no problem. Height 56, length 36, and weight 23 centimeters, also no problem. But here comes. Your baggage should be 150 centimeter in dimension. If anybody knows, you can send me an email later. If anybody knows what that is supposed to tell me, I would love to know, because I've been sitting with this for a long time and I still don't know what it is. So units are crucial and important, and they're to a large extent the foundation of where we go from there. Now, I want to address the question of how we actually ask a question properly for an experimental design. Let's do this. We're going to imagine the following kind of experimental setup. The research background is that we want to investigate the effect of climate change, and we know that climate change is expected to lead to a rise in temperature. The task would be, say, to test the effect of temperature on the metabolic rate of a fish species. Our first proposed design would be, we take the normal temperature, which is today's average. We take a medium one, which is between today's average and the highest value we would expect. And we take the highest temperature, which is our expected values in, say, 50 years from now. Go back to our descriptions and our definitions. What's the independent variable? Temperature. What's the dependent variable? Metabolic rate. And a suggested test would be something like exposing fish to different temperatures and using an analysis of variance, or the alternative depending on how the data are distributed. We'll go back to our template one more time, and that is your null hypothesis was that there is the same metabolic rate for medium, high, and low temperatures, and the outcome of the analysis of variance can tell us whether there may be an effect of temperature, but it does not tell us how that effect worked and where it is. It only tells us that there may be one if we reject H0. So that's good information, but not in any way complete. So what's our possible problem with this design? We work on a predicted temperature in 50 years from now, and a prediction is never actually a very good thing, because we haven't actually got any confirmation that that's correct. And you don't extrapolate beyond your existing data set anyways. So we also don't know whether the metabolic rate is linearly related to temperature. So this kind of design doesn't yet actually tell us how temperature does affect metabolic rate. Can we do it better? Can we redesign? Maybe we could. And we would have to ask the questions right. We would have to ask it in such a way that we can actually answer it best. And that is, the question would be, what is the relationship between metabolic rate and temperature? And now we can do a design where we test, for example, even 10 temperatures and determine the metabolic rate for each with a smaller number of fish. Temperature is now considered a continuous variable, and the outcome could be kind of a regression model, like I explained earlier. And that would allow us to give an idea on how the temperature affects metabolic rate, and we can use a nice wide range of values. Later, we can then still ask simple questions like, are these values within the range of values that we would be expecting for climate change? But the experiment is much more meaningful because we've actually tested a good question, which is the relationship between those variables. So the next thing that we must look at is what do we do when we design experiments? And my summary at this point is that we have to randomize, that we identify pseudo replication, which I talked about, and that we make sure that we choose our controls and then analyze our data correctly, and that we decide before a study sometimes, depending on how it's appropriate, which pairwise comparisons we will be able to make. I have already mentioned the concept of correlations, confounding factors. And those are factors that are part of our experiment that we also refer to as nuisance factors. And they don't allow you to actually properly analyze your data unless you have figured out what these factors do. Here, I've given you some examples here, for example, assigning cages and experimental units to one part of the room incorrectly, or to feed some animals first and then some other animals later and do it consistently the same. Then you don't know whether you're actually testing what you wanted to test or whether you're testing the feeding. From other disciplines, say, for example, you conduct phone interviews, but you choose only one time of the day in which you do it, then you would also then by default only get a certain group of people that will be at home at that time of day. And whatever answer you get from your phone interviews will actually not be representative for people in general, because the ones that aren't there, they weren't interviewed. Or, for example, if you do a study where you select from volunteers rather than from a randomly chosen group of people, maybe volunteers for a study are already biased for something, or maybe they are not really representative for the whole group. So again, it can then become a confounding factor for your study, depending on where your samples come from. Or sometimes you may have studies where you ask people questions, but you do it in the wrong sequence. You ask a particular question first, and then depending on how you ask it, another answer comes up for another question. And the only way to get around this is to at least do random assignments where you spread the error that is inevitably in your data sets. You spread it across different kind of conditions so that you don't have these factors confounding your results. It's a very challenging and tricky thing to do. One more issue to bring up is the issue of correlations between continuous data. Here's a nice example. If we go to the data from a beach, and we have the number of shark attacks, and they are correlated, as you can see quite nicely actually, to the ice cream consumption at the beach by people who visit. It's a wonderful correlation, isn't it? It's really great. But if we now say that the ice cream consumption has an effect on shark attacks, we would be completely wrong, because we would be confusing correlation with causation. In other words, we would actually not do justice to such a data set. And as a second thing that I wanted to show you in this graph is that my choice of units on purpose is incomprehensible. I'm not giving you proper units. What do I mean by ice cream consumption? What do I mean by shark attacks? So these 2 points must be considered in with regard to what you actually do when you analyze correlations. The first thing you need to know is, are the correlations that you find between data really there, or are they just having to do with other factors? The simple answer in this example, you probably guessed it by now, is, well, the more ice cream consumption there is, the more people will be at the beach. That means the more events of shark attacks can happen. But they're not related to each other. The one is just unrelated to another, only that the correlation analysis gives you the wrong idea. So if you're ever stuck with correlations, always have another really careful look at, first of all, what units you're looking at, and second of all, what you're actually comparing with each other. So reporting results present a good and clearly defined hypothesis. That is the most important thing for all result sections, and of course for the design as well. Don't be shy. Show the variability in the data. Sometimes it may be a bit uncomfortable, and you might feel like maybe there's quite a bit of variability. That is information. Don't discard it. Just let it be seen. Let it show it, and make sure that you show and describe the sample sizes and what experimental units you have used. Describe how you randomized your technique, your samples. That's true for just about any survey or experiments you do. And also test the assumptions of the tests. That's now statistics that we don't all discuss today, but make sure that your statistical test does justice to your data. An important part is if you have data sets in which there is no significance, that does not necessarily mean that there is a lack of importance. So not having a significant effect can, in some cases, actually be very much worthy of mentioning and worthy of reporting. So don't be discouraged if you don't find that. But it's always, of course, much more exciting if you do, because then you found a certain effect of something on something that you can then report. And a high level of significance may not always be as meaningful as the actual differences between treatments. I will give you an example of that in a moment. So having put together the first steps of the experimental design, gives me an opportunity to summarize what we have been talking about until now. And that is that for any experimental design or for any data set that you use, you will be doing yourself a great favor if you always go back to that point where you say, what is your dependent and what's your independent variable? And what type of data do you have? Continuous data, frequencies, categorical data, etc., etc. There's a whole range of those. Once you know this, you have a good foundation to find out what statistical test you use. With this, you understand why it is so important to use hypotheses, and Also, I hope I gave you a little bit of a background as to where this concept of a hypothesis kind of really came from and why it is so different from the very early ways of looking at data in which we just simply make statements and say A causes B, so I'm good enough with that. And the reason why we have hypotheses is because everything has somehow some error involved in it. I see that from our timing that we would have more or less 5 minutes left, and I think this would be probably a good time to let you off on this one, because there was anyways a plan for a second seminar next week at that time, and then I can continue with biases and various other issues about analyzing data that we haven't all discussed yet. So for now, whoever has been hanging out with me for so long, I can only say thanks a lot for taking the time to listen, and I hope that you might also get maybe a little bit as excited as I always have been about designing and analyzing experiments, because there's a lot of fun in there, and there's a lot of good ideas that we follow in order to get some interesting and useful results, and then report them to the rest of the world when we write our publications. And these are things that I will actually then discuss in the next session, according to the plan. Yeah, thanks.
Thank you. No, that was really, really interesting. There were a couple of questions in the chat, and I'm wondering if we can just take a couple of minutes to just see if maybe they were answered, or if people still want to ask them, if that's okay, just really quickly. Is that all right?
Yes, the only thing is that I don't see the chats right now on my screen.
Okay. Well, basically,
I have to search for that. Yeah.
James and Deepa had questions. So can I just ask the people who did ask questions? Mfono Bong had a question as well. There were just 4. Has your question been answered, or do you just want to ask your question of Horst in the last few minutes before we have about 9 or 10 minutes before 4:30? So Fense asks, other than increasing the likelihood of error and making it harder to account for confounding variables, why would too large a sample be an issue? And then James asked, is the number of replicates, does that mean the number treated versus untreated? And then Nandeepa's question was, what determines a sample size to be used for a particular question or research problem? So those were the 3 questions.
So the first one is probably to a large extent, the most difficult one. And that, I think, if I recall now, the question was, is too large a sample size a bad idea?
Yeah, why would it, other than increasing the likelihood of error and making it harder to account for confounding variables? Why would it be?
Well, as far as, okay, let's look at it from 2 angles. If you work with animals, then you want to keep the sample size low enough so that you don't have to use any more animals than you need to. So that answers part of the question. But if you have other kind of experimental designs in which that wouldn't play a role, then a larger sample size will certainly ultimately reduce your error to such an extent that your analysis is more likely to give you significant effects. But it does not necessarily have any effect or any impact on reducing the importance of confounding factors. That's unrelated, because confounding factors can be in a small or a large sample size. They must be cut down as much as possible. So a large sample size won't rescue from that problem. But the issue is, it's quite a deeper issue. if you dramatically increase your sample size, for example, you might also find effects that are in themselves quite small and still significant. To give you an example, let's say you weigh several thousand mice, and you have a certain weight, and you weigh several thousand mice from another environment, and they will be only by maybe 1% bigger. It will inevitably be significant, but in this case, significance isn't necessarily saying that it is meaningful or important. It is just significant. So we can easily confuse these two things. So the best sample size is determined. I think that answers the second question, or that brings up a comment to the second question. The sample size is determined by knowing the variability in your data up front. You don't always know, so sometimes you don't have a choice. But if you do, there is ways of calculating beforehand what kind of sample size you would need to have a good power in your analysis or in your test. And the third one, as I said, didn't see the chat, so I'm not quite sure where that went now.
The next question was, I think you answered, well, Nandeepa, you must tell us if we've answered your question. But the other question was, does the number of replicates mean the number treated versus untreated in that example that you gave?
Treated versus untreated in my example was 2 replicates for treated, 2 replicates for untreated. So that is still 2 replicates. If we have, say, four cages treated, 4 cages untreated, we have 4 replicates per treatment. Ideally, we should always have enough replicates, like 2 or 3 is a very small number, and it doesn't always help us. But sometimes we are a little bit stuck with the logistics and the infrastructure, and we can't do much better. But the number of replicates belong to a treatment.
Okay. James, have we answered you? Can you let us know in the chat? And then the final question, I'm not sure if James answered Mfonabong's question because he did type an answer, but is the p-value of 5% a given or constant, or is it calculated from the data on a particular piece of research?
Oh no, the p-value is the direct result of the calculation. Okay. All right. So you can have any p-value that differs from somewhere close to 0 or close to 1.
Okay.
Neither of them is actually real. So exactly 0 doesn't really make sense, but it can be extremely close to 0, or it can almost be 1. So within that range, and that is the result of your calculation, right?
All right.
And the crucial part is, and I was hoping to discuss that as we continue, the most important part is the question as to why we use the 5% as our cutoff point. The person who actually invented this 5% rule, that was Sir Ronald Fisher, who invented statistics to a large extent. And when he was asked in an interview why he chose 5%, which the rest of the world obviously is following, he said, oh, that was kind of my good guess for this one. So the 5% rule has become a standard for all the work we do, yet it does not have a really strong motivation. Maybe from now on, we should do all experiments at 6%, and then everybody would agree, and that's fine. But I wanted to discuss this issue then as we continue with the next talk, because that's also something that is currently very, very heavily and deeply discussed.
Right. Okay, so we'll pick that up again next week.
I think so.
Okay, and then there's one last question, which is Fence again asking, why is an optimal sample size between 10 and 30? He says, I've seen this around a couple of times in some reading, although obviously it depends on the context of your research as to what an optimal sample size is.
It does, but it brings you back to a statistical concept, which is the concept of the normal distribution. And ideally, we should have data that are normally distributed. And in order to know how well they are normally distributed, we should have we should obey the central limit theorem, which means a sample size of 30 or over. We often don't have that.
Right.
We don't have it, but ideally we should, but it's not always possible.
Okay. Well, thank you so much for answering, and thank you for your questions in the chat, and thank you, Horst. I found that a little bit bewildering as a social scientist myself, but also quite interesting because I'm trying to learn a bit more about regression analyses and these kinds of things. So I enjoyed that. Everybody says thanks very much for answering their questions and for this session, and we obviously will look forward to part 2 next Thursday, same time.
I think that's the plan, yes. And we will communicate about this, and if anything changes, then we'll know. But yeah, that makes sense, yeah.
Great. All right. Well, thank you all very much. Enjoy the rest of your weeks and weekend, and hopefully we'll see many of you back here next Thursday for part 2 of experimental research design. Thank you and good afternoon.
Okay, thanks to everybody for coming.
Thank you. Bye-bye.
All righty. Bye.